Good morning, everyone. My apologies for having to provide a pre-recorded presentation, but hopefully this goes well. And if you have any questions, please reach out to me. I'm Ernest Bell, and I'm a postdoc at the NASA Goddard Space Flight Center, working on an application of terrestrial geophysical studies of lunar analogs to lunar surface science operations. I'd like to acknowledge my survey GEODES colleagues listed on this slide, and especially Nick Schmer, the GEODES PI, as well as the coordination with the RISE-2 team in conducting this study. Today I'd like to brief you on the GEODES team's use of co-located geophysical surveys at the Kilbourne Hole Maar crater as an analog to conducting similar studies on the lunar surface. First of all, our scientific objective for this study is to use a combination of multiple geophysical techniques to investigate the four primary strata: ash, consolidated surge beds, the basaltic lava flow, and the underlying fluvial sedimentation found on the rim of Kilbourne Hole Maar crater. From an operations perspective, our objective is to use the planning and execution to aid in the translation of terrestrial field geophysical studies to lunar surface science operations. Terrestrial volcanic fields provide excellent lunar analog environments for these studies, as the methods used are similar to those that have and will be used on the Moon. These include methods such as active seismic, ground-penetrating radar, and magnetometry techniques. As mentioned, our field site for this study is Kilbourne Hole, which is located within the Potrillo volcanic field in south-central New Mexico. Kilbourne Hole, shown on the right, is an approximately 2 to 3 kilometer diameter crater of a Maar eruption and has been used for training purposes by NASA since the late 1960s. For our scientific investigation, we used several geophysical techniques. These were an active seismic investigation using up to 48 geophones at 2-meter spacings, 200 and 400 megahertz GPR data collection, and total field magnetometry. Each of these techniques were applied across 4 different transect lines. We also collected samples of each of the 4 strata found to be used in geophysical laboratory testing. As can be understood, the various techniques can have competing constraints that preclude simultaneous operations, such as seismically quiet area for the active seismic data collection or a magnetically clean area for magnetic surveys. From the scientific operations perspective, we underwent an evolution of concept of operations to address competing requirements from constraints on instrumentation use, as well as the number of personnel required for each task. Pre-field deployment planning included initial potential locations for conducting the surveys, which can be seen as the blue lines in the lower right aerial view of Kilbourne Hole. These data collection locations can be described as crew-executed transitory transects. The boots-on-the-ground field plan called for a day of scouting the possible sites to down-select to those necessary to obtain the data for each of the strata. This would be followed by executing 2 strategies for gathering data. The first of these was to be single-site operations where we collected the data and samples largely in series to avoid competing instrumentation constraints. The second of these strategies was to divide and conquer, where we would split the instrumentation and a team between 2 sites for simultaneous data collection with instrumentation having competing operational constraints. As for the actual field execution, our boots-on-the-ground field scouting resulted in 2 sites that would provide access to all strata of interest. Site 1 in yellow was located on the southeast corner of the crater and consisted of 3 parallel lines, one on the surface of each of the top 3 strata: ash, surge beds, and a basaltic flow. Site 2 in red was located on the southwest corner and allowed direct contact with the fluvial sediment layer. Use of these 2 sites resulted in a morphing of the single-site ops and a divide-and-conquer strategies. Single-site ops, or serial execution of the 3 geophysical techniques, were conducted in series for each of the 4 transects. While these were conducted, sampling proceeded in parallel in a divide-and-conquer strategy near Site 1, where there was easy access to all 4 layers. So in conclusion, the execution of terrestrial field geophysical research provided an opportunity to conduct coordinated sequencing and prioritization of fieldwork that is analogous to future lunar surface studies. Also, the evolution of our pre-field deployment plans during the actual field campaign is analogous to possible evolution of future lunar surface mission operations. And finally, the lessons learned and best practices we developed from executing terrestrial studies in lunar analog settings can be applied to developing future concepts of operations for human lunar mission surface science. With that, thank you, and please reach out to me or the Geodes team with any questions you may have. Thanks. Have a great day.